Well, good morning, everybody. Sorry for the slight delay there. Technical hitch already. This morning I've been asked to really just give a little bit of background and a little bit of information on something that's been going on in the UK for the last, I guess, 14 or more years, relating to safety of plant on site, and particularly provision of working platforms for tracked plant. Well, why this presentation? Although fatalities due to rigs and track plant toppling over are rare, they do happen. And we know, this is not new to any of us, I don't think, that worldwide, the safety record for the construction industry is very poor. So if we can raise awareness of safety issues, make our sites safer, we can reduce the economic and the human cost of poor working platforms specifically. And who knows, through today, we actually might save somebody's life down the line. So I just want to cover some experiences really with what we've found in the UK, and particularly through an organisation called the Federation of Piling Specialists, which is a UK organisation. It's affiliated to the EFC, which is European Federation of Foundation Contractors, and it's a trade organisation that is really comprised mainly of practitioners. So they developed a working platform initiative, and it's a whole process. And so I want to cover a little bit of background about what that process looks like for us, and then go into a little bit more detail regarding one aspect, which is if you're going to design a working platform, you've obviously got to know what loading is applied to that platform. And then we have a spreadsheet tool, which is freely available, which I'll go into in a little bit more detail. And then once you've obviously got the loading, then just a little bit on how the platforms are designed. Now, if we go back to early 2000s, it was recognized that the incidence of piling rigs falling over because of poor platforms was just really too high, and it was something that we could do something about. So that's why the Federation of Piling Specialists, the FPS, launched their working platform initiative. And they wanted, obviously, to promote safety, but they wanted to try and do it in a way that was economic and sustainable. They did a lot of work themselves, but then engaged an organization called the BRE, which stands for Building Research Establishment, which was at that time a quasi sort of government body that held the leading position in research and development in the UK. And they published a document, a little book called Working Platforms for Tracked Plant. Now this appeared in 2004, and in the time since 2004 and now, the whole process for providing working platforms, not just for piling rigs and the like, but it's sort of seeped out into wider industry. Obviously, cranes are the sort of next thing you might start thinking about, but also track plant and raised platforms, wheel platforms and that sort of thing. Also are covered now by some of these aspects. Okay. In terms of creating a safe working platform, there are numerous facets, numerous aspects to consider. And I sat in yesterday at the working group meeting here, and we were kind of talking about sort of bubbles, and within each bubble are different sort of areas and aspects of creating a process to improve our safety. So one is the legal framework. Another aspect is what is your contractual and commercial relationship with your client, and I believe you've got on your construction sites or in your construction projects you have the controlling entity, who is the person who's kind of overseeing the whole site. What's your relationship with them? And you know, my experience working I worked for many years for Keller in the UK, and you know, as a subcontractor, you feel like you're down at the bottom of the food chain sometimes. So how do you influence? Then obviously, if you're going to design a platform, you need to know what forces are being put on that platform. So that has to be considered. And then you have to do some calculations to come up with the platform thickness. The construction of the platform obviously has to be in accordance with the design. And one of the challenges is that we can do a design based on a borehole or a trial pit that's at one very discrete location. But if we've got, I don't know, 40,000 square foot site for a warehouse or something, how do we make sure that our design section is applicable across the whole site? How do we inspect the formation before we put the platform down to make sure we haven't got any unforeseen holes or service trenches that have not been properly backfilled? So construction is a very important aspect, as is validation. How do you validate your platform? In the olden days, it was the foreman's boot, the heel of his boot, but really, I think we've all realized that kind of doesn't really cut the mustard anymore. And then once the platform is being used, it has to be maintained and, if necessary, repaired. There was one UK incident where there was a piling site, and the platform had been put down in a good way, had been well designed, the rig loadings were understood, and a piling rig went over. And later investigation, it turned out over the weekend, somebody had to come in and do a service diversion, which they had done. They hadn't fully backfilled the trench, although they had reinstated the granular mat over the top of the trench, and the rig, when it tracked over that improperly backfilled trench, went over. And all of these little bubbles fit in a bigger bubble, which is, you know, we've got to try and be cost effective, and we've got to really be trying to add value as well as making things safe. And of course, there's another thing that we often don't consider is our moral obligations. And I'm kind of quite big on this, really, for no other reason other than we want our guys and girls on site to come to work in the morning and go home at the end of the day. If we can improve the chances of them doing that, that is good. I read a horrendous statistic. I was looking at the United States, I think it was a website for Department of Labor, and it was saying over the lifetime of a construction worker of, say, 45 years, there's a 1 in 200 chance of them being killed. And I'm not saying the UK is significantly better, and other parts of the world are significantly better, because we know that worldwide construction is not as safe as it should be, but that's a horrifying statistic. So I just want to outline now a little bit about the UK legal framework, because this is the way we do it, but if other people are going to kind of take on some sort of process and initiative, it's going to have to be framed to suit your environment. So we have what we call the client, who's the person who's developing a site. They have responsibilities under law to make sure they are appointing people to look after health and safety. At the design stage, pre-site work, there's an entity called the principal designer, and they have to identify, eliminate, and control the risks that they can foresee. And if there are sub-designers, the principal designer has to make sure that they are fulfilling their roles. So you can argue that the principal designer is also responsible for ensuring there's enough ground investigation information to design a safe working platform, because they have to have thought, how can whatever they're designing be built in a safe way? And then when it gets to construction, you have a principal contractor. Now, this may be your controlling entity. I'm not sure whether it's that person or whether it's the client. But when it gets to construction, they are responsible for planning and managing and monitoring all aspects of health and safety. And then if we have our specialist geotechnical contractor, they will sit underneath the principal contractor, They do have responsibilities to make sure their work is carried out safely, but that was with underneath the umbrella of the principal contractor. And really, when it gets to site, it's the people in that red cloud, and it's that area that we're often talking about where we're operating in. Okay, so the main process and components that we follow is, firstly, you need to establish a process, and you need to establish who is responsible for what. Once that's done, then you get into the nitty-gritty technical stuff. You can establish the site conditions, so you need to know what the ground is, and topography is also very important, particularly if there's going to be cutting and filling going on, because the borehole or trial pit commencement level may not be your working platform formation level. Then you obviously need to design the platform for your known loadings, and we'll come to that in a little bit more detail in a minute. Then you design your platform, so you obviously assess your subgrade strength, you select your platform material, and if you're going to use geogrids or geocomposites, select what they might be, and then do some number crunching, some design calculations to give you a platform thickness. But it doesn't just stop there, as I've already said. It's very important that there is competent installation. So you need a specification, there needs to be some sort of quality control. There needs to be some definition of the working area and testing maybe of the platform. And that vigilance needs continuing through operation, maintenance and repair. And to embrace all of these different aspects, you need some sort of management stroke control system. In the UK, that's done through a very simple form. We call it the Working Platform Certificate. And I'm led to believe that the word certificate can have a bit of a loaded legal connotation in the US. So you could call it the Working Platform Form. Perhaps there's too many forms. But something simple to help us guide us through the process. It summarizes what the project is, what part of the project you're working on. It summarizes what loading the working platform has been designed to operate under. It puts the designer's name, and that's an individual. So we're identifying and naming individuals now, creating where the responsibility lies, the designer organization, and any testing that is required. And then the principal contractor, which maybe in your circumstances would be the controlling entity, has to sign in ink or blood to say that they are confirming the platform has been correctly designed, correctly installed, and will be correctly maintained before the piling contractor goes onto the site. And in 2004, the FPS had created an earlier version of this form, and they collectively said, we are not going to work on sites unless the principal contractor has signed this form. And at that time, there was a lot of wailing and gnashing of teeth, particularly from maybe some less well-informed clients. And they said, oh, this is dreadful, this is dreadful. But the FPS members stuck to their guns. And in time, it's been recognized throughout the industry, not only for FPS members, but also non-FPS members now, that they're not going to go on site unless this form has been completed by the principal contractor. Okay, so just to summarize the process, or perhaps show pictorially, once you've established your responsibilities from a design point of view, establish your ground conditions, determine your rig loading, do your calculations to determine what your platform thickness is going to be, have some construction done by a competent person, validation perhaps is required, and then you use, inspect, and maintain until the end of the life of the platform. And that's all overarched by this management and control process. So The title, I think, of my talk this morning was prefaced as a workshop. And what I want to do now is actually go through, very quickly actually, a tool that's freely available. It's an Excel spreadsheet tool, which was developed by the FPS in the early 2000s and has undergone some fairly recent revisions to make it a bit more user-friendly, etc. But I think it's going to be quite difficult in this environment to really get down to the nuts and bolts of that. But if you've got internet connection, you may go on to www.fps.org.uk, and then you will find there's the website, which if I go forward, looks like that. And you can click on the little button and you can download the spreadsheet for free. And there's guidance notes there as well, and some examples. So the spreadsheet tool comprises, as I say, Excel forms that you complete. And the aims of the tool really were to try and make it as simple as possible to use, something that would give consistent and reliable results, and it would cover most of the usual piling rig situations. It's routinely used for the larger rigs, even 100-ton rigs, down through the more sort of routine that we have in the UK anyway. I think you call them auger cast piles, we call them CFA piles, CFA piling rigs, sort of anything from 80 down to 30-odd ton machines. It's also used for the mini rigs, so going up from the 1 to 2 ton machines up to the all the way up to the 100-ton machines really. And it's the most usual situations, so it's really implementing the 80-20 rule. There will always be exceptions, but these need to be considered as exceptions, and again by a competent person. As I said, the tool's freely available, and there's some guidance provided. And in the UK, we do run training courses, and they're usually sort of half-day long, and people actually come along with their laptops and are guided through examples, given the theory and the background. So that then means that people are being trained in the use in a consistent way across the country. The tool was developed by engineers, including a lot of people on the plant health and safety side of the construction industry. And it has a distinct purpose. It's to assess the bearing pressures that are applied by rigs on granular working platforms. It's not used to establish inherent rig stability. There are other codes and standards that do that. And really, the term competent person is quite crucial here. And my definition is a competent person is somebody who will have knowledge, hence the training, and some real-world experience of what rigs look like and how they work. Okay, so we've just seen that's the spreadsheet. Sorry, that's the website. If you go to the FPS website, you can click one of the little boxes and download the tool. So what does the tool do? Okay, it calculates the track, and if you've got footpads or outriggers, their bearing pressures. It considers all the different modes of operation of a rig, and if it's a slewing rig, all the slew angles. And then the output, obviously, has to be compatible with the platform design method. And if we go back to the document BRE 470, working platforms to track the plant, which again, you have to buy it, I'm afraid, but you can buy it off the internet from the BRE website. Does give a design method. There are other design methods as well, the actual working platform. Essentially, the spreadsheet has sort of 3 main components spread over a number of worksheets. The first, as you'd expect, is the data entry, Obviously, you're not going to be able to read this, but you can see it looks fairly daunting, but isn't really that daunting when you get into it. So you put basic data in there. There are then provided with the sort of routine download 6 spreadsheets that will consider different modes of operation of a rig. So there's the standing mode, there's the traveling mode, so that is the rig obviously tracking around. Handling, which may be for preform piles, precast piles, tubular piles, can be quite critical. Could incorporate unloading from lorries and what have you. Then there's the penetrating mode, the extracting mode, and I'm going to come and talk about those in a bit more detail in a minute because they're treated quite specially, the penetrating and extracting modes. And then you've got a spare spreadsheet, but if you know the password to unlock the spreadsheet, you can of course add many more operating modes if you want. And then there's an output summary. So some of the basic assumptions that we're working with here is that your rig is working on essentially a flat, horizontal working platform, not on a steep slope. And we use a rule of thumb of about 1 in 20, anything less than 1 in 20 gradient as being considered as flat. And the forces derived from the use of the rig are vertical. If your winch forces, the assumption is that they are operating vertically and you haven't got large lateral loading. And that your rig is not going to be exposed to high wind loads, high slewing loads, and high dynamic force loads. Now, the resistance to the rig, the thing that stops it falling over, is provided by the tracks. And if you've got any outriggers or footpads, they're also considered. As I've already said, that masts and winches considered to be operating vertically, you'd have to go in or do some pre-processing if you're going to start imposing lateral or semi-lateral loading. The forces that we will use to calculate the bearing pressures are derived by statics, so fairly basic engineering and maths. And obviously another assumption is, and it comes back to the use of the competent person, that they know what they're doing. So in terms of input information, you need to know from the rig the various components of the rig. And this is just a figure taken from the guidance notes that's available on the website there. So, for example, you'll need to know what the weight of the tracks is, and the tracks are the non-slewing components of the rig at the bottom, the main body of the rig, counterweight, all that sort of stuff, which are part of probably the slewing components, mast, etc. You need to know their weights, and you need to know the distance from the center of rotation of the rig, or the centroid of the tracks, where those weights are applied. Finding that information from rig manufacturers' documentation has improved quite significantly. Most modern rigs, certainly within Europe now, and their manufacturers will provide this information quite readily. Maybe if you've got older rigs, or if that information is not so readily provided by the rig manufacturers, you might have to go to the time and effort of taking bits of your rig off, weighing it, and measuring where its center of gravity is with respect to the middle of the tracks. The other things you need to know are track dimensions, and then any forces and the points of action of those forces generated by any winches. So that's a slightly larger shot of the data entry sheet. Pressure calculation, which covers the different operating modes, And this is really the engine of where the calculations happen. And the basic principle is that we just consider the static equilibrium equations of the rig in its working configuration. So whether it's standing, it'll have certain forces applied. If it's traveling, it'll probably be the same forces applied actually as standing. But if it's handling, penetrating, or extracting, there may be winch forces that we need to consider. And we can consider them fairly simply, really. We can, because we know the weights of the different components and we know the distance of those components from the centroid of the tracks, we can take moments, and we know our vertical equilibrium equations because we know the rig is sitting on a platform, and we know the resistance. Some of the resistance generated by the platform has got to equal the weight of the rig plus any winch forces. And if we've got a foot pad, that's also part of the equation. Now, the trouble is, if we've got a rig with 2 tracks and 1 foot pad, and we look at our equilibrium equations, we discover that it's a statically indeterminate problem, so we can't solve the equations. And the way around this was to allow the operator to impose a foot pad resistance. And by doing that, we render the equation statically determinate, and we can solve the problem and then work out what the bearing pressures are. Now, it's really very important just to remember that when we put in our foot pad resistance, when using the tool, it's only a device to make the equation statically determinate. Whether that foot pad will ever feel that load, we will rarely find out. And what we do within the tool, when we impose the load, the foot pad load or foot pad resistance, is we iterate till we get to a point that the bearing pressure under the foot pad equals the bearing pressure under the tracks, and then design the platform for that bearing pressure and the worst case loaded area. So the calculation principles are, as I said, we input the component weights and their coordinates on an XY sort of grid, assuming in the first instance that the slew angle of the rig is 0 degrees. We input a foot pad resistance if the foot pad is indeed being used. If it's not being used, then obviously you don't put it in. Then we can work out the net downward force, which is the red blob, and its point of action in a coordinate form. And from that, we can work out what the resistance needs to be provided from the tracks. We can take moment to see whether there's more load on one side than the other. We work out where the resistance on the tracks is with respect to the track length. If it's right in the middle, the shear or the bearing pressure distribution under the track is just rectangular. Obviously, if that point of action or point of action of that resistance moves away from the center of the tracks, the bearing pressure distribution first becomes trapezoidal and then can become triangular. And if you've input stuff wrong, or you're trying to work out a calculation where actually the rig's unstable, the point of action or point of resistance would fall outside the track. Now, the spreadsheet tool, basically, if you get to that point, stops working and you won't get an answer because something is obviously clearly wrong. Once you've worked out, once the spreadsheet has worked out the stress distribution under the track, that's equated to an equivalent rectangular distribution, fairly basic soil mechanics. And then that process is carried out for every angle of slew for a slewing rig. Obviously, if the rig's not a slewing rig, you only need to do the one calculation. And the output looks like this. And as you can see right at the very top of or near the top of the table, you've got a slew angle of 0 degrees. And in this example, you've got on the right-hand side of the table, in the sort of orangey color, you've got the bearing pressure calculated, which is 94 kilopascals, and a track length of 2.87. Now, as the rig slews, you can see the track bearing pressure varies, which is kind of what you would expect. And towards the bottom of the table, it's just outputted what the maximum values are for this particular mode of operation. And this table and these calculations appear on each of the operating mode spreadsheets. Now, there's another element that has recently been introduced to the spreadsheet, and that is, it was felt that sometimes the people doing the working platform design, and in particular, working out the bearing pressures, weren't necessarily sure under a given operating condition how close the rig might be to the resultant resistance falling outside the footprint of the tracks, and hence the rig would be unstable. So this measure called the eccentricity index was introduced, and really it's just a measure of where that resultant force is. That's the red blob within the footprint of the tracks. It has to be emphasized that this is not about calculating the inherent stability of the rig, because to do that, certainly in European standards, you have to calculate something called the stability angle, which is no help to us as designers of working platforms. So the eccentricity index is there, and basically it's just the ratio of where that resultant action is with respect to the track footprint. If the value is 0.33, it means that resultant is in the middle third. If it's between 0.33 and 1, it means that the rig is probably stable, but you may end up having a triangular distribution of pressure under the tracks, with the implication that the rear of the track is lifting. And there are various warnings in the spreadsheet that highlight that situation. It doesn't necessarily mean that it's unsafe to operate the rig in that condition. It's just a warning to flag that. And obviously, if the eccentricity index was greater than 1, it would mean that the rig had overturned, and the spreadsheet will not return a result if that situation arises. Now then, with the penetrating and the extracting modes of operation, in order not to become overly conservative when applying winch forces, a couple of little tricks were implemented. Now, if the rig is in the standing mode and the head and the digging tool or auger or whatever you're using on the Kelly bar is withdrawn and above ground surface, obviously the weight of that suspended equipment, and that's how it's termed in the spreadsheet, forms part of the rig weight. And we've, in the input page, put in the weights and points of actions of those bits of equipment. But when you start penetrating, the weight of that suspended equipment can be considered to be taken by the ground, because it's actually in the ground and resting in the ground. So your rig weight effectively becomes slightly lighter. And this is considered within the spreadsheet. Now, if there is no crowd force and you're just resting your tools on the ground, your winch force, which is shown in the yellow cell with the red circle around it at a very small value of minus 0.01, means there's no crowd force. And when you look across to the left, the net penetrating force is minus 70, and that balances the weight of the suspended equipment. So there's a couple of things that need to be considered here, is that when inputting the information in the tool, you need to know what your suspended equipment is, where it is, and define it. Put it in the tool correctly, so that these efficiencies, if you like, on subtracting the weight of that equipment when working out the bearing capacity when penetrating and extracting can be correctly implemented. Now, if you have a crowd force, and this is an example of a 29 kilonewton crowd force, what you find is that your net penetrating force is minus the weight of your suspended equipment with the crowd force summed up with it to give, in this case, a net penetrating force of minus 99 kilonewtons. And when extracting, a similar process is followed. With the tools in the ground, the net extraction force that you're putting on your winch to lift the tools out of the ground, firstly, part of that force is simply taking the weight of that suspended equipment, and because you've already accounted for it, you don't want to double count. And then only the leftover force that's available to overcome soil resistance, etc., needs taken into account. So in this example, though our winch force applied is 392 kilonewtons, the weight of our suspended equipment is 70 kilonewtons, and we don't want to double count. So our net extraction force is 392 minus 70, 322. And it's very important that the operator of this tool understands what's going on here. On the topic of foot pads and how we deal with those, as we said before, inputting the value of foot pad resistance is a device to render the equilibrium equation statically determinate. And what you do is you input the pad size and location in the input sheet, and then in the selected mode sheet, you would input a trial force, observe the change that generates in the track pressures, iterate until you're getting a balance. So that might look something like this. On the left side of the screen, you can see the mode sheet, and you can see here that we've got an applied foot pad pressure has been input of 200 kilopascals, and foot pad area is 1.5 meters squared. And then on the right, we've got the calculation of the track pressures, and at the bottom, it also shows the 200 kPa that's been put in as the pad resistance, and that has been iterated. Now, we haven't quite got a balance. We've got 207 kilonewton per meter squared on the track and 200 on the foot pad, but that's near enough for a platform design. So that has to be borne in mind as well. So once you've done your calculations, the results are summarized on the summary sheet. There's a summary of the input data, and it's often only this sheet that's given to the actual platform designer. There's a summary of the output data and error messages and notes. So if something's gone wrong, there are some error messages and various notes, like, for example, if the tracks have got a triangular distribution, it's called track lifting, just as a flag, really. So zooming in on the output data, you can see on the left the different modes of operation, the equivalent track length calculation, track width, bearing pressure. And in this case, what we note is the greatest bearing pressure is on the extracting mode. This is for a CFA rig. So it's sort of what to be expected. And then you will note there's a comment that's called BRE load case 1 or 2. And I'll come to that in a second or two. Then there's the eccentricity index, looked at parallel and perpendicular to the tracks, and those are all okay. And just for information, there's just the sum of the winch forces, just to make sure that you're aware of what winch forces are being applied and they're not unrealistic. So once you've got that summary, you can go and calculate the thickness of your platform. I say BRE 470 does give a fairly straightforward method, just standard soil mechanics really. But the method uses characteristic material parameters for the platform and the subgrade, and then certain loading factors are applied. And these really are empirical loading factors. They don't tie in with any design standard, any European design standard, but it felt that they were appropriate and matched experience, and they've been used successfully, say, over the past 13 or so years. And there are two cases considered. There's case 1 where, in the operating mode of the rig, if it were to start to tip, the rig operator couldn't do anything about it. So, for example, if they were traveling and the rig started to go, there's very little, or probably nothing, the operator can do. And so a loading factor of 1.6 is applied to the bearing pressures. And where recovery is possible, for example, if you were extracting and the operator felt the rig starting to tilt excessively, they could let go and ease off on the crowd force. So those loading factors tie into the BRE load case 1 or load case 2, and it's therefore just important for the platform designer to understand which load case the pressures that are output from the spreadsheet tool relate to, so they know which loading factors to apply in their calculations. And it's also worth mentioning that although the BRE method has got a design approach in there, you could use other methods. So, in summary, the FPS tool calculates the bearing pressures for the purpose of giving them to the granular working platform designer. The input data is component dimensions and the weights. It's based on a rig working on a horizontal granular platform. If you're applying foot pads, just remember that that's just a device to enable equations to be solved, and you need to know what you're doing. The eccentricity index might be a helpful just cross-check that the rig appears to be working in a stable fashion, but it does not replace a rigorous stability check. And there are, certainly in Europe, different standards that cover that. And the tool is freely available. The FPS took the view that although they don't represent every piling contractor in the UK, safety was too much of an important thing to be parochial about. And so the use of this tool fits in with this wider managed process undertaken by individuals who have clear responsibilities, using common input parameters, using a published calculation method, and verified construction and maintenance. And that's all managed by an overall control process. And we're now 13, 14 years since the publication of BRE 470. It did drive industry change. Safety has been improved. The approach does have now a track record, and it has gained universal acceptance in the UK. If you find it helpful, bits of it helpful, please feel free to take all, some, or none of what this approach sets out. Thanks very much. Thank you.